The fourth step of plotting graph is locating tabular values on the axis. After we calibrate the two axes, we notice that every interval has a number appended to it. What it means is that every interval has a value. What if we see a table whose values we want to plot on the graph page? And we discover that some of the values we want to plot are not clearly marked on the axis after calibration. How do we locate the exact position of each value on the table on the axis? That takes us to lesson number 14, and that is locating tabular values on the axis. Please notice how I use an existing problem, a foregoing case, to explain how to locate tabular values on the axis. Please follow through.
Okay, as you can see on the screen, it says to locate a figure on the axis, use the formula. And what's the formula? Capital N is equal to V over small b. What does N mean? What does V mean? And what does B mean? You will get more confused if I try to use this formula alone to explain what it is. Instead, I have chosen to explain it more fully with examples, starting with our foregoing case. But before then, let me briefly say what each symbol stands for. This V, see it here, stands for the figure being located. That is, that figure which you see on the table, whose position you want to know on the axis. Next is this B. B is the value of one unit box along the axis. Not everywhere on the graph page, but along the axis. And then this capital N, see it here, is equal to the number of unit boxes from origin, which must be counted to reach the figure. Like I said earlier, it is better we practice using it than taking our time to give examples where talking about them alone may not be enough. But before then, still, separately, this B has its own expression or its own formula. B, recall, is the value of one unit box. That is, one unit box along the axis. What value corresponds to it? It has its own formula. What is it? It is equal to S over small n. What does this S mean? S means the scale, and n means the number of unit boxes in one interval. In fact, as long as a particular case is concerned, both S and n are constants. Why? To start with, this n is number of unit boxes in one interval. Recall that once a graph page is written, n is fixed already. The graph page we're using has 10 unit boxes to make one interval. It is a 2 cm interval. Therefore, n automatically, for our foregoing case, is equal to 10. Then, after scale is chosen for a particular case, that scale remains constant throughout the time we shall need it. Therefore, both the scale and the number of unit boxes are constant. Because of that, the value of one unit box will also be a constant. Based on this, is it this or this we start with when we want to start locating tabular values on the axis? We start with this. When we start with this, B is equal to S over N, we get the value of one small box, and we indicate it on each axis. It is after we have known B that we cannot place it here. This is now what we use afterwards. So the first step is find this. When we find this, we now take the value of B and place here. And then from here, that point onwards, it is this we're going to be using until the end of locating tabular values for both X and Y axis. Let us use the foregoing case, the case of plotting the table we have been plotting before, to see how exactly this formula can be used. Let's see. What you see on the screen is a procedure for getting the formula for finding a value on the table along the x-axis. Don't forget I said earlier that the formula for finding the location where a value on the table is on the axis is n is equal to v over b. Right now, the first thing we do is to find a value of the b, where b stands for the value of 1 unit box. That is, this b refers to the value of this one small box here, so that each place you go to, if you count 5 boxes, you will know what the value will be. Later we'll get back to this point. Again, we recall that the formula for finding the unit box is equal to scale over number of boxes in one interval. Don't forget that the scale for this x-axis is 1. From here to here is 1. Therefore, this s has become 1. Then this n refers to number of boxes in one interval. From here to here is one interval. How many boxes are there? There are 10 of them. That is why I placed 10 here. I hope you're following. Now, let's calculate 1 over 10. Why did I write this b subscript x here? It is because b stands for any small unit box, whether vertical axis or not, whether it is horizontal axis or vertical axis. B is B, the value of 1 unit box. But now we are concentrating on the value of 1 unit box for the x-axis. That is why I brought this x here to be its subscript. I hope you understand now. So bx is equal to 1 over 10, and therefore bx is equal to 0.1. It therefore means that any small box here is equal to 0.1 unit. Don't forget, we don't know what x represents. We don't know the physical quantity that x is measuring. Therefore, whatever quantity it is, it has a unit. That is why we say unit. So each box here is 0.1 unit, which means if you count one box, 0.1 unit, there are 2 boxes here. We now have 0.2 unit, 0.3, 0.4, 0.5, 0.6. That means each small box is 0.1. This is the most essential stage of plotting graph. That is knowing the value of 1 unit box. I repeat, this is the most essential stage. That is finding the value of 1 small box. Now we have seen it in this particular case as 0.1. Let's continue. Now that the value of 1 small box is known, go back to the formula for locating tabular values and replace the b with 0.1. That gives us nx is equal to v over 0.1. b used to be here. Why x here? The same reason why x was introduced here is why it is introduced at this point. We are counting the number of small boxes to locate a value. What it means is that whatever value you're looking for, place it here and divide by 0.1. Whatever it gives to you, you count it. We're going to come back to using it afterwards. But at this point, just know that this is now a formula for locating every value on the x-axis. Every value on the x-axis. That is, nx is equal to v over 0.1. Let's do a similar thing for y-axis. See it here. The formula for finding the value of one unit box remains the same thing. The scale over number of boxes in one interval. For this y-axis, the scale is 4. That is, the value of one interval is 4. That is why this scale must be replaced by 4. See it here. And we have 10 unit boxes in one interval. Yes, because if you count from here to here, that is one interval. You have 10 boxes. Also from here to here, 10 boxes. So in every interval, there are 10 boxes. Therefore, the small n is equal to 10. So scale is 4. Small n is 10. Now calculate 4 over 10. It is equal to 0.4. Therefore, the unit value for a unit box along the y-axis, that is b subscript y, is equal to 0.4. I hope you know how this was gotten and that you are following. Now, ultimately, we have it that the number of unit boxes we count to locate a value is equal to v over 0.4. Meaning, whenever I want to locate a value along the y-axis from the table, what you do is just that value you want to locate, place it here, and divide by 0.4. Whatever it gives you is the number of boxes you must count to reach that value. Likewise, if you want to locate a value along the x-axis from the table, place the value you want to locate here and divide by 0.1. Whatever it gives to you, that is number of boxes you must count from the origin to reach the value. Let's put these two formulas into work. From now on, until we locate all the values, it is these two formulas we're going to be using. Don't forget that finding the value of one unit box is the most crucial or the most essential stage of plotting graph. Let's make progress. To constantly bear it in mind and use it in locating values along the x-axis, the formula is written here at the edge, the very edge of this graph page towards the left or any other extreme along the x. That means it is possible to write this either on the left side, the leftmost part of this graph page, or rightmost part of this graph page. In this case, I chose to write it here on the leftmost part, and that is v over 0.1. Very soon you see how this plays out. The same thing applicable to the y-axis. See it. You see it at this point, it is v over 0.4 for locating values along this y-axis, and v over 0.1 for locating values along the x-axis. Let's continue. Now, let us locate these values of x along its axis. Let me start with this negative part. First, we have minus 3. It is true that minus 3 is here. But what if it had not been here? How do we know that minus 3 is at this point? Minus 2 is also here. Minus 1 is also here. 1 is here. And 2 is here. Does it mean that this formula is useless? You might think it is useless because of the fact that all the values of x in the table are also found on the axis. That is not always the case. Let us use this formula to authenticate its usefulness. First, I want to locate the position of this minus 3. If what I get at last is the same thing as where minus 3 is, that will tell you how authentic this formula is. This minus 3 is the value we're looking for. If I place minus 3 here, or just place 3, don't forget that we are dealing with magnitudes here. That means I'll just place this 3 here and say 3 over 0.1. Let us see what it's going to be. 3 over 0.1 is equal to 30. 3 came from here to replace this v. That is here. 0.1 is still where it is. See it here. 3 over 0.1 is equal to 30. Please confirm. What does this 30 therefore mean? It simply means from origin, count 30 unit boxes along this negative x-axis. The 30th box, stop there. That is the place that this 3 is found. Let us count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Instead of counting until 30, we just bear it in mind that from here to here, that is this interval, contains 10. That means from here to here is 10. 10 boxes, 20 boxes, 30 boxes. That means we are correct. That means on the 30th box, stop. That is where minus 3 is found. And exactly, that is what we found. Let's check the place where this 2 is located. To locate these 2, we replace this v with it, so that this 2 becomes what is here. That is here. And 0.1 is still where it is. 2 over 0.1 is equal to 20. 20 what? 20 unit boxes. Meaning that we have to count 20 boxes from this origin. The 20th box, stop there. That is where 2 is located. From here to here is 10 boxes. From here to here is 10 boxes. That means altogether we have 20 boxes. And this is where minus 2 is located. Is that a coincidence? No, it is not a coincidence. Let's now locate this minus 1 in like manner. To locate 1, we replace this v with 1. That is this minus 1 here, is what is here. Don't forget we deal with magnitudes, not a sign in this calculation. So we have 1 over 0.1. 0.1 had been there. So, and 1 is what we're locating. That's the value. 1 over 0.1 is equal to 10. 10 what? 10 unit boxes. Counting from where? Counting from the origin towards the left. Let's count. From here to here is 10 unit boxes. And that corresponds to where the minus 1 is. Just count 10 boxes. The 10th box, stop there. That is where minus 1 is located. And truly, that is where it is. I hope this is getting interesting. Let's now locate this 1. Just the same way. Let's see. 1 over 0.1 is equal to 10. But this time around, we don't count towards the left because 1 here is positive. That is this 1 here. It means count 10 unit boxes from the origin towards the right this time around. And on the 10th count, pin it there. That is where 1 is located. From here to here is 10 unit boxes. That is where 1 is here located. The same thing applicable to 2. We have done 2 before. The same way. 2 over 0.1 will give us 20. That means from here to here will be equal to 20 unit boxes corresponding to the position of these 2. I hope you've been enjoying the procedure. Let's do the same thing for y-axis. For y-axis, we recall that the formula for finding the location of every value is v over 0.4, where v is the value you want to locate. For y-axis, look at all our v's. Minus 19, minus 13, minus 7, minus 1, 5, and 11. They are all the values we're going to locate with respect to their positions along this axis, both this minus y subaxis and the positive y-axis. We're going to start with the first value on the y-axis to replace this v. And if we do that, this minus 19 takes the place of v, so we have minus 19 over 0.4. Don't forget how this 0.4 came to be. Let's continue. Minus 19 over this 0.4. Whether it is minus or not, please, the answer we're going to get must not matter. In fact, to avoid doubts, we simply say 19. Let us take away that minus. That has been done to avoid confusion. That minus is simply serving us a purpose to tell us that that 19 is on the negative part of the y-axis. Now, 19 over 0.4 is equal to 47.5. What are we doing with 47.5? It means count 47.5 boxes from origin along this axis downwards, and then when it is completed, point it there, stop there. That is the position or the location of this minus 19. This minus 19 we are seeing here. Let us see how they count them from the origin. The origin is here, and we now count 47.5 boxes. From here to here is 10 boxes. 20. Are you following? 30 boxes. I hope you know why. Each interval contains 10. 40 boxes. This is the 40th box. The next is to make it 47.5. Remember, here is the 40th box. We now count 41, 42, 43, 44, 45, 46, 47. 47 is here. What about the half? The next box is broken into two to make it the half. Look at its position. A position has been indicated with a dot, a bullet point. This is the position or the location of minus 19, just a short distance before minus 20. This is wonderful. This formula helps us to get the exact location of a value. You see, we got for 7.5, that is for 7.5. Sometimes we wish to use only whole numbers in locating this. Yes, sometimes we prefer to use whole numbers instead of mixed number like this. This is for 7.5. That is a mixed number. 0.5 means half. We can approximate it mathematically to 48. That is, if we don't want to use fractions like this. If we want only whole numbers without using fractions, this will become 48 small boxes from origin to the point, so that I would have kept this bullet point exactly at this point. But as you can see, the bullet point is kept midway. That is half of this small box. This is more accurate than the one we get after approximating this to 48. But both of them can serve us. Let's now locate this 13. Let's see what it turns out to be. Again, the value, this is 13, is going to replace this v so that we have 13 over 0.4. It is equal to 32.5, meaning count 32.5 small boxes from origin. Whatever it ends, stop there. That is the location of this 13. Let's do it. From here to here contains 10 small boxes. Another 10, that is 20. Another 10, that is 30. So the 30th box is here. But we have 32.5. That means I will count 2.5. That is 30 now. 1, 2. That is 32. Okay, 31, 32. And then half. The same thing that happened before will happen. Once you see 0.5, it means half of that small box. Then 0.1 means 1/10 of that box. 0.2 is 2/10 of that box. 0.4 means 4/10 of that box. And in that manner. But here, 0.5 means 5/10. That is a half of it. That is why we divide this small space into 2. Let's see. Let's use a slash instead of a dot or a bullet point to differentiate what we're locating right now from the former positions corresponding to the marked values on the axis. 12, 8, 4, and the rest were marked with bullet points. Let us use a slash to differentiate these marked points from calculated positions. We use a slash for such positions and a bullet point for marked positions corresponding to values on the axis. Now, we see that this 13 over 0.4 is equal to 32.5. That is here. I used a slash for doing it. Let us now locate this -7 along this axis in like manner. We have it that this 7, which replaces this v, is 7 over 0.4 when substituted, and we have 17.5. That is, count 17.5 unit boxes from this origin downwards. Whatever it ends, stop there, and that is the location of this -7. Let's count. From origin to this point contains 10. The next is 20. That means that it has crossed 17.5. So we start counting box by box after crossing the first 10. From here to here is 10, 11, 12, 13, 14, 15, 16, 17, then 17.5. Let's see how it goes. So that is the position of 17.5. I hope you're following what I'm doing here. Now, let's turn attention to the next one, which is this -1. What is -1? Let's find out. So we have it that this 1 is found, that is, each location is found by replacing a v with it. So we have that this v is equal to 1. So 1 over 0.4 is equal to 2.5. 2.5 what? 2.5 unit boxes, counting downwards from the origin. Let's count. 1, 2, then 2.5. This is the 2.5 position. Let's mark it. Again, like others, you have seen it marked with that slash. So this is the place we have marked to correspond to this minus 1. Next is this 5. Let's do the same thing. We'll now locate the value of this 5 this way. Let this 5 replace this V so that we have this V being 5 now, divided by 0.4. And so what you have there is equal to 12.5. That is, count 12.5 unit boxes. This time around, no longer below the origin, it's above the origin because this 5 is positive. So we count from here upwards. 12.5 unit boxes. When we count that number of boxes, we stop. And that is the location of this 5. Let's try and do it. From here to here is 10. That means the next is 11th position. We now have from here to here 10, 11, 12. Then 12.5 is the next box broken into half. That is this position. Let's mark it. So here is the position of 5. Just a short distance after 4, you get the 5. What about the location of this 11? If something is going to happen, let's find out how we go about it. Now to locate this 11, we replace this V with it. So we have 11 over 0.4. 11 divided by 0.4 is equal to 27.5, meaning we count 27.5 unit boxes from this origin upwards. Whatever the number of boxes ends corresponding to the 27.5, we end, and that is the location of this 11. Let's do the counting. From here to here, 10. Then from here to here also, 10. That's 20 now. 21, 22, 23, 24, 25, 26, 27. Then next is 0.5. That is the next box divided into 2. It appears that throughout this process, we've been having 0.5, 0.5 each case along the y-axis. Do you think that is what you're going to see in everything you do during your own personal practices? The answer is no. This is just a coincidence. Do not think that you will always see 0.5 in your own case, no matter what the case is. Let's now mark this position corresponding to 11. Surely, this is the position of 11. It hasn't been marked like others. Notice also that there is no value on this table corresponding to y that was found already marked along the y-axis. For this 19, we had to carry out calculation before locating it. The same thing happens to 13, 7, 1, 5, and 11. All these 6 values were calculated respecting their positions. But don't forget that whether the value we see on the table is marked along the axis or not, we can make it more authentic by using the formula V over B. At this point in time, the next level is locating the partial points of intersection. So far, I believe that this process of locating tabular values has been exciting.